The human brain is an extraordinary organ that enables our intelligence, allowing us to learn, understand, and apply knowledge in various situations to make informed decisions. This video will provide insights into how the brain functions. Our brain is constantly active, continuously firing electrical signals through neural circuits made up of interconnected neurons, with up to 20% of them active at any given moment. Let's explore the fundamental building blocks of the brain. At the core of the brain's function are neurons, specialized cells that form the basis of its complex network. Evolutionarily, there are many types of neurons, but approximately 80% are pyramidal neurons. The brain houses over 80 billion neurons, organized in intricate patterns. Neurons communicate through electrical signals. These signals are received by a branching structure called dendrites, which accumulate electrical potential. When this potential crosses a certain threshold, the neuron's axon generates a signal, propagating it through the neural circuit. Axons, resembling electrical wires, can penetrate different layers of neurons, enabling long-range connections. Each neuron acts like an arithmetic unit, continuously deciding whether to fire based on the inputs it receives. Neurons form circuits through connections called synapses. Synapses can be newly formed, modified, or removed depending on the neuron's activity. They can be either excitatory, increasing the electrical potential, or inhibitory, decreasing it, thereby influencing the likelihood of the axon firing. Active neurons tend to have more vibrant synaptic activity, supporting learning and adaptation. Evolution has crafted a remarkable variety of chemical mechanisms around synapses, enabling the dynamic processes of learning and memory. Each neuron connects to thousands of others via synapses, with an average of 10,000 synapses per neuron, resulting in an astounding 800 trillion connections within the brain's electrical circuits. This synaptic network is the foundation of memory formation, with synapse creation and modification directly linked to learning. Today, this cellular-level learning process is well understood, shedding light on how the brain continuously adapts and evolves. Now that we've explored how neural circuits are constructed and dynamically adapt, it becomes easier to understand how the brain interacts with the world through our senses: sight, hearing, touch, taste, and smell. In each case, light, sound, or chemicals are converted into electrical signals by specialized sensory cells. For example, our eyes move about 3 times per second, scanning the environment to create a dynamic visual pattern. Interestingly, the brain has a clever way of tricking us so we don't notice this constant motion. What's truly fascinating is that all sensory inputs, whether light captured by our eyes, sounds detected by our ears, or sensations of touch, smell, and taste, are processed in the same way. They are all transformed into spatial patterns of electrical signals that continuously change over time. The human brain is remarkably uniform in its structure, with 6 distinct layers of neurons, organized into structures known as cortical columns. These columns are the foundation for processing incoming information. What happens next, however, is even more extraordinary. Patterns of input signals are transmitted through a hierarchical network of neural columns, where each level specializes in increasingly complex tasks. This hierarchy, a result of evolution, allows the brain to extract progressively abstract and detailed features from input signals. For instance, primitive animals perceive only basic features like lines, while more advanced brains use hierarchical processing to identify complex shapes and objects. This principle is especially well studied in vision, where regions in the brain known as V1-V5 process visual data, from detecting simple edges in V1 to recognizing complex shapes and motion in V5. Building a model of the world. As patterns travel through this hierarchy, they leave footprints in the neurons by forming corresponding mirror synapses. Thanks to the immense number of neurons, the brain can store an almost infinite variety of such patterns, enabling us to build a detailed model of the world. This model represents processed input at different levels of abstraction, ranging from simple geometric lines to the perception of colors, faces, and complex shapes. Unlike modern AI systems, the human brain can learn and adapt to virtually any input or environmental change. This remarkable adaptability is known as brain plasticity, the ability of the brain to reshape its synaptic connections in response to new experiences. However, this flexibility has limits. Some regions of the hierarchy remain adaptable throughout life, while others, such as those related to fundamental skills like language, are more rigid after early developmental stages. It's similar to a house. You can renovate endlessly, but the foundation remains fixed unless you rebuild it entirely. The role of hormones in learning and adaptation. An important factor in brain plasticity is the hormonal background and its influence on learning cycles. For example, during sleep cycles, inhibitory connections dominate, allowing the brain to consolidate memories and prepare for new learning. When we encounter familiar patterns, learning happens at a slower, more relaxed pace. However, when faced with novel or unexpected stimuli, such as spotting a new car on the street, our hormones activate the brain, accelerating the learning process. Over time, as the stimulus becomes familiar, the brain calms down again. Babies exemplify this high learning state as their brains are constantly stimulated by new inputs, driving rapid development. During the day, excitatory connections predominate, enabling active learning, while at calmer moments, inhibitory connections take over, temporarily blocking synapses and slowing the process. Storing memories and shaping personality. All the patterns we learn are stored in the brain as a hierarchical network of synaptic connections, forming our internal model of the world. This model is incredibly adaptive, but significant changes, like moving to a new city, can be stressful as they force the brain to rapidly update its structure. At the highest levels of the hierarchy, the brain integrates sensory inputs from various modalities and combines them with emotions, storing these as memories. This integration shapes our personality and emotional responses. For example, the taste of black caviar might evoke indifference in one person and excitement in another, depending on their individual experiences and emotional associations. From input to behavior, the brain processes input and generates output in a structured way. Sensory signals arrive primarily at the back of the brain, where they are processed, while motor outputs are formed in the front of the brain, near areas responsible for thinking and planning, the core of what we call intelligence. Behavior arises when spatial and temporal patterns of brain activity flow backward through the hierarchy to activate muscle receptors. This process requires learning and refinement. For instance, a baby must spend time and effort, often through trial and error, to learn how to walk. Once a goal is achieved, the rate of learning slows, but encountering new challenges or bumps reignites the learning process, aided by hormonal signals. Abstract thinking and continuous learning. Abstract thinking operates similarly. When you look at the sun and then close your eyes, you can still visualize the image in your mind. This is because the brain never stops processing and learning, even in the absence of direct input. In fact, thinking often becomes easier when external input is minimized, a state known as distraction-free learning. The ease or difficulty of abstract thought depends heavily on our hormonal background, which influences how efficiently we can shape and refine our mental models. A dynamic adaptive system. The brain's extraordinary ability to integrate sensory inputs, store them hierarchically, and adapt its internal model of the world is the foundation of our intelligence, creativity, and behavior. While it shares similarities with AI networks like convolutional neural networks, CNNs, the brain's adaptability, plasticity, and emotional integration make it far more complex. This dynamic system not only processes input signals with unparalleled sophistication, but also shapes who we are, how we think, and how we interact with the world. Through constant processing, the brain stores input information at various levels of its hierarchy. Together, these countless patterns form what we call our model of the world, a dynamic framework that helps us navigate and make sense of our environment. This is why familiar places, like returning home, bring a sense of calm. The brain processes already known patterns, requiring minimal effort. In contrast, sleeping in a new hotel can be challenging because the brain becomes more alert, working to learn and adapt to unfamiliar surroundings. Each new pattern introduces a certain level of stress, which explains why humans often resist change. It disrupts the brain's established model. Thanks to the properties of neurons, our brain is incredibly adaptable in learning new patterns, a phenomenon known as neuroplasticity. This flexibility allows us to continually acquire new skills and knowledge throughout life. Babies, in particular, are remarkable learners. They absorb information by watching, imitating, and experimenting, guided by positive or negative reinforcement. Every small success fills them with joy as their brains reward the achievement of new milestones. If you found this video helpful, don't forget to click the like button and subscribe to our channel to stay updated with our latest releases. Your support motivates us to create even more exciting and insightful content for you.